Hello, this is Jim Corkins, and we are moving on to 1.4 in Kinematics, and this is relative motion. Again, if you haven't done the reading, please do so. OpenStax 2 and 3 if you're in Physics 111, and OpenStax 2, 3, and 4 if you're in Physics 121. And if you have the CLETA textbook, this would be chapters 1, 2, and 3. And please get started on your homework. Okay? All right. Well, relative motion is just that. There is a reference frame that we have to consider. And so typically when we think about motion, we think about if you're driving in your car, you think about your car moving and the earth and everything outside is standing still. But it is just as reliable to think of the earth moving and you're standing still, okay? Since things are relative, that means they have a reference frame. You could consider yourself a reference frame of moving relative to another reference frame that is not moving. And that other reference frame may or may not be moving too. And so also, you have to also consider, too, that there could be multiple reference frames, like 2, 3, 4 reference frames. And it's always important to consider one of the reference frames as not moving and the other two reference frames or the other reference frames as moving. So you're going to always want to keep, if you have multiple reference frames, you always want to keep one of the reference frames not moving. Okay? So here to illustrate this is, suppose this person is standing by some train tracks and you have a train moving just to the right, okay? And the train is moving at a speed of 15 meters per second. And I'm going to click to mark up this document, and now I have my tools ready. So here's the train's speed right here. And this is TG. Why is it TG? I don't know. Anyways. This is the person on the train. V, person on the train. And this is VTG, which is the train itself. Should just be V sub T, but okay. I think they're doing train to ground. Okay, so the train is moving at 15 meters per second. And here you have a person on the ground, and they're not moving. Okay, so this person is not moving. So they are the reference frame that is not moving. And here you have a person that is moving on a train, and they're walking at a speed of a positive 1.2 meters per second. Again, to the right is positive x, to the left is negative x. Okay, so they're walking to the right at positive 1.2 meters per second, and the train is moving at 15 meters per second. Well, from the person who is standing still, this person is not just moving at 1.2 meters per second. This person's moving at 1.2 meters per second in reference to the train. So that means, compared to the person on the ground is going to actually see this person moving at 1.2 meters per second plus 15 meters per second. Okay? And that's because the train is moving. So overall, this person on the train is going to actually be moving at what is that? 16.2 meters per second to the right. Okay? So that's what this person here on the ground is going to be seeing, that the person on the train is going to be moving actually at 16.2 meters per second. Okay? If the person was walking to the left, well, they would have a negative velocity, because to the left, if your velocity vector is to the left, that is in the negative x direction. Okay? And if the train is moving to the right at 15 meters per second, well, the person on the ground is going to be seeing this person on the train moving at a total speed of, what is that, 13.8 meters per second in the positive direction. So even though they're walking to the left, overall they're going to be moving to the right at a positive 13.8 meters per second relative to the person on the ground. And so that is essentially relative motion. Okay, you have a reference frame of somebody standing still, and they're measuring the motions of other objects relative to their reference frame. So if you want to consider yourself a reference frame, it's probably best to consider yourself not moving and everything else moving. So even if you're sitting in a car, maybe consider yourself not moving, and that means if you're driving your car forward, all the shops and things on the road are going to be coming at you, so they're going to have a negative velocity towards you. So their velocity is going to be directed towards you, and you are not moving. So it's kind of helpful sometimes to think of things that way. So you always have to consider relative motions of objects, okay? So here we have the velocity of a reference frame, the velocity in a frame moving up and to the right. And we have the velocity of the frame itself, which is moving just to the right. So if you want to transform everything relative to this object, okay, so this object is now going to be standing still, and it's going to be the frame of reference. What you need to do is you need to set that guy to be standing still. So your frame is moving inside, the frame itself is moving to the right, and this object is moving up and to the right in the frame. So to get it to stand still, what you have to do is you basically say this object is moving up and to the right, and this is going to be the transformation of the frame. Okay, so this is the frame of reference for it to be standing still, and what you're going to have to do is consider the frame of reference. So in other words, what you're going to have to do to solve for this frame of reference to be standing still is you're going to have to subtract the frame moving to the right from the object moving in the frame up and to the right. Okay? And so that means you have to reverse the direction of this vector and then add it to the velocity of the object moving in the frame. Okay? And when you do that, what you get is you get this transformation, right? So it all leads right back to vector addition. Okay? And that's kind of what we're doing. So we're trying to, we're making, doing some algebra transformations, algebraic operations, and then we're doing a graphical analysis, okay, with vectors, right? And this will become more clear. I don't want to, this is a little abstract, but I just want to give you the basic tools, talk about the basic tools of frame transformation. So to bring it down to its most essential terms, let's just keep everything in one dimension for right now, and let's talk about it. So Lucy's holding a ball in her hands inside a truck, which is moving at 6 meters per second. So what is the speed of the ball relative to Lucy? So go ahead and answer that question. So Lucy's holding a ball in her hands, okay, and she's not throwing the ball or anything like that. And the truck is moving at 6 meters per second. So what is the speed of the ball relative to Lucy? So Lucy is the frame of reference. All right. Well, if you think about it, the ball is not moving relative to Lucy. So even though they're both moving to the left at 6 meters per second, the ball here would not be moving. So the velocity of the ball in reference to Lucy is going to be 0. Ball relative to Lucy. Okay, so I subscripted it. Okay, and so we're going to build upon that. So Lucy's holding a ball in her hands inside a truck moving at 6 meters per second. So what is the speed of the ball relative to John, who's standing still? So John is going to be looking at the speed of the ball relative to John. So we need to know the speed of the ball relative to John. Well, the ball is not moving. The ball's velocity relative to the truck is equal to 0. But the truck's velocity of the truck relative to John is going to be equal to negative is going to be negative 6 meters per second. And so what that means, the velocity of the ball relative to John is also 6 meters per second. So the velocity of the truck relative to John is 6 meters per second, but the ball is not moving in that reference frame. So overall from John is going to just see the ball moving at negative 6 meters per second, even though it's not moving in the truck, but the truck is moving to the left. Okay? And so now Lucy's going to be the reference frame. Okay? So now the velocity of the truck relative to Lucy is equal to 0. But the velocity of the truck relative to John, actually to the ball, John is now holding the ball. This is John over here. John is holding the ball, so the velocity of the truck relative to the ball is going to be negative 6 meters per second, because the ball is moving to the left. Okay? But from Lucy's frame of reference, she's moving to the left, and she's got the reference frame now. So she's actually seeing the ball, velocity of the ball relative to Lucy is going to be equal to positive 6 meters per second, right? Because she's moving in the truck to the left, but the ball is now, if she's now considering herself standing still, she's just going to see John and the ball moving to the right. Okay? So that's kind of the basics of reference frame transformations. You have to think of everything relative to something else. So that's why I was doing truck to Lucy, truck to the ball, ball to Lucy. Okay? And so here we have another situation that is very similar to what we just did. Okay, so now we have a person, so we have a car, a red car that's standing still. Okay? So this is our reference frame, and so notice that they actually do put an X, Y on the reference frame here. So this red car is not moving. Okay, and now you have a blue car that is actually driving at, it's moving at a positive 90 kilometers per hour. So it's moving at a positive 90 kilometers per hour. And you have another blue car in C that's moving to the left at negative 60 kilometers per hour, right? So reference to something that's not moving, these transformations are kind of easy, right? But if you make your reference frame now this blue car, so that means you're considering the blue car not moving, even though it is moving at 90 miles an hour. We're going to be considering everything else is moving relative to it. So if this car is moving forward at 90 kilometers per hour, I said miles per hour a second ago, I'm sorry. So it's moving to the right at 90 kilometers per hour. If we consider that these people are saying that everything else is moving around them relative to them, then that would mean this blue car is going to be traveling to the left at negative 90 kilometers per hour. And that would mean this 60 kilometers per hour car that is traveling towards it is now going to be traveling towards it even faster because its frame is moving to the right. So that means it's going to make this guy's frame even more faster to the left. Okay, so that's the relative motion. So this is going to be negative 60 kilometers per hour minus a 90 kilometers per hour. While this one is just going to be negative 90 kilometers per hour plus 0 kilometers per hour. So you're actually I got that reversed. To get this guy's frame, want to do the actual object's actual velocity first, and then take off the new reference frame's speed from that. Okay, so you do the object's actual velocity relative to 0. Okay, and then you take off this guy's speed from that. You take the relative part as negative or positive relative to that. Okay, so I hope this kind of helps you a little bit with one-dimensional relative velocity and how to set a reference frame. But what I want to do is move on to two-dimensional relative velocity. Okay, so again, you have a person on a train. In this case, the person on the train is going to be moving upwards. Okay, so this person is climbing at some speed only in the y direction. So it'll be in the positive y direction, positive x direction, and the train is moving in the positive x direction. Okay, well, this person is standing still, so they're the still reference frame. So from their perspective, they are going to see this person moving to the right on the train, but also moving up. So this person is actually going to be moving up and to the right relative to the person standing on the ground at some angle theta, right? And that angle theta would be, the inverse tangent. So theta would be the inverse tangent of opposite, which would be the VPT over the VTG. Okay? And to get the person's overall velocity moving up and to the right, VPG, you would have to go, VPG is going to be equal to the square root of VPT squared plus VTG squared, right? So that's the most basic form of relative motion. It gets a little worse. Like if the person was actually moving up and to the right on the reference frame, you would have to figure out their velocity in the x direction and their velocity in the y direction, and then add their x direction velocity to this velocity, to the velocity of the train itself, and that would be their overall horizontal velocity. And then you'll have to get their velocity up and to the right as well. So there's a lot of things that you have to think about when you're doing this relative motion, and it's going to be leading on to projectile motion, and I'll show you in a little bit how that works. But let's practice relative motion a little bit more, because this is going to be helpful when you get in, if you ever do relativity stuff. There's reference frames in relativity. That's important. So again, to go over what we just did for relative motion in 2D, so if you have an object that is moving with a velocity v prime relative to one frame of reference, and that frame of reference is moving with a velocity v, capital V, well, then to get the velocity of the object relative to a new frame of reference, what you do is just add those two velocity vectors, right? But if you want to get everybody's velocity relative to the object that is moving, you're going to have to subtract off that frame right here. So you're going to have, in this case as an example, you have a jetliner that is going to be flying at 960 kilometers an hour relative to the air northward. So that means they're going to be flying, if the air is moving to the right at 190 kilometers per hour, they're going to be needing to fly at some angle somewhat eastward, okay, at 960 kilometers an hour, to take into account that velocity right there, that velocity of the air, because they just want to be moving straight upwards, right? So if your goal, this plane wants to fly directly upwards, right? But the air is pushing it to the right. So what they're going to have to do is fly at some angle, and we'll find out later on it's 11 degrees, but they're going to be having to fly to the eastward and upward at 960 kilometers per hour. right? So there's a little bit of trigonometry involved in this, right? So if this is the hypotenuse and this is the so this is the hypotenuse and this is opposite this angle theta, to get theta there, well, that is going to be the sine of theta is going to be equal to 190 kilometers per hour, the velocity of the air, divided by 960 kilometers per hour for the velocity of the plane. And so to get theta, you're going to have to take the inverse sine of those two things, right? Inverse sine of the velocity of the air, velocity of the plane, right? And now to get the speed at which it's actually going to be flying straight upwards, right? So here's Los Angeles, and here is Hawaii, right? And they want to, well, actually, I should say Los Angeles and maybe Seattle, because Seattle is directly north of Los Angeles. Well, if the air is moving eastwards, right, and they want the plane just to go straight upwards, well, they're going to have to correct for that air by flying slightly westwards, right, because the air is moving to the east. Okay, this is north. Never eat sour watermelons, right? So they're going to be flying slightly westward to correct for that air. So now the plane should just be moving straight upwards. Well, they need to fly at this will work out to be 11 degrees, right? At 960 kilometers an hour. And then once they figure that out, now they could figure out their speed going straight to Seattle along this line. Okay, which would be this is going to be this is C, this is A, and this is B. So you're going to need to do C squared equals A squared plus B squared, which we need to get B. So this is going to be C squared minus A squared is going to be equal to B, and we're going to take the square root of that, right? So to get this velocity right here, this velocity is equal to the square root of 960 kilometers per hour squared minus 190 kilometers per hour squared, right? Because C is a hypotenuse, A and B are the sides, right? And so if C is a hypotenuse, then we're going to have to be subtracting that hypotenuse, one of the sides from the hypotenuse to get that other side. This is a 2. Okay? So this stuff is really important if you're a pilot and you need to plot a course straight upwards, but you have to take into account wind and air. And this reference frame stuff is really important. Okay? Because if the plane just started flying northward, right, if you didn't consider the air and you wanted to fly the plane straight upwards at 960 kilometers per hour, you would end up right over here. You would end up eastward of Seattle, and then you'd have to travel just to the left at 190, well, actually at double 190 kilometers per hour to get to Seattle, right? So and so I wouldn't want to take that path because you'd be traveling a hypotenuse plus this. Well, it's easier just to fly the plane up and to the left and that would make the plane just go straight upwards because the air is pushing it to the right. So that last problem is kind of a forerunner into what we're doing here. So here's a great example that we should all try. And this is all relative velocities. Okay, so now let me help set this up. So you've got a river, okay, and a river is flowing. This river is flowing at 1 meter per second to the right in the x direction, okay? You have a person who is paddling their boat, and they're rowing their boat upwards at a speed, and they're just rowing straight upwards at a speed of, and I'll put the speed over here, at 3 meters per second. Okay. Over here, you have a person number 2 who is walking, and they're always going to keep the boat to their left. Okay, so you have to think about how fast would they have to walk in order to keep this boat just on their left as they're walking downstream. And you have a person here, person 1 is going to be walking along a bridge that's always going to want to keep their boat on the right. So how fast are they going to have to walk in order to keep this person on their right hand side? Okay. And then over here you have another person who is standing still, so this person has no velocity. And so what do they see of the velocities of the person 1, person 2, and the person in the boat? What do they see as their overall velocities of these people not moving? Well, person number 1, in order to keep the boat on the right, just to the right, they need to be walking at a speed of 3 meters per second upward. Okay. And person number 2, in order to keep the boat on their left as they're walking downstream, needs to be walking at the speed of the stream itself, which is 1 meter per second. Okay, so person number 1 needs to walk at the speed that this person is rowing to keep them on the right, and person number 2 needs to be walking at the speed of the river to keep the boat on the left. And so person number 3 is going to see the boat moving up and to the right, is going to be moving up at 3 meters per second, but also moving downstream at 1 meter per second. So they're going to see the boat moving at a speed, they're going to see the boat moving at a speed in this direction. They're going to see this boat moving off in that direction. And so they're going to see this overall speed to be equal to, well, this is the hypotenuse in this case, so this is going to be c. So this is the overall speed of the boat relative to person number 3, and that would be square root of 1 meter per second squared plus 3 meters per second squared, right? And so what is that number? So 1 squared, so that is what? 9 plus 1, so that's a square root of 10. So 10 square root, so 3.16. So they're going to see the boat moving at 3.16 meters per second up and to the right. Is going to be the velocity of the boat relative to person number 3. Okay, so person number 3 is standing here. They're seeing the boat moving up and to the right, and they're going to see them moving at this angle theta, and that angle theta is going to be the inverse tangent of opposite. Opposite that angle is this side, which is 1 divided by 3. 1 meter per second divided by 3 meters per second. So that angle theta is going to be, let's see here, pull up my calculator again. So is that 1 divided by 3 equals, so that's 0.3333, and then we got to do inverse tangent of that at 18.43 degrees. So with objects moving in 2 dimensions, and you got to consider reference frames. So from reference frame from person, if you put the reference frame number 1, if you put the reference frame around person number 1, they're going to be walking at a, they're going to see person 3 moving down at -3 meters per second. They're going to see this boat just floating to the right at a positive 1 meter per second. And they're going to also see person number 2, they're going to see person number 2 moving down and to the right, because they're walking up, but they're considering themselves standing still. So this person is going to be -3 meters per second, the boat is going to be moving at a +1 meter per second, because the boat is always on the right, so it's just flowing with the river. And person number 2, they're moving up, but they're trying to keep up with the boat, so they're going to be moving at 3.16 meters per second down and to the right. And at that angle right here, which will be theta, which will be 18.43 degrees, right? And person number 2 is going to see the boat, if they're now the still reference frame, they're going to see the boat just moving at a positive y direction at 3 meters per second. They're going to see person number 3 moving to the left at a -1 meter per second. And they're going to see person number 1 moving up and to the right, because the person number 1 will eventually be up here, up and to the right at 3.16 meters per second at an angle of 18.43 degrees. Okay? And finally, if we consider the boat is going to see, if the boat is now the still reference frame, the boat is going to see person number 2 moving down at -3 meters per second. It's going to see person number 1 moving to the left at -1 meter per second. And the boat is going to see person number 3 moving down and to the left at -3.16 meters per second at an angle of 18.43 degrees. So that's basically how you go through everybody's relative motions to each other by shifting that reference frame. Okay? And this is kind of basically what we did, right? If you have a ball or a hockey puck or something like that is moving up and to the right, well, this if the reference frame is right here, relative to this object, again, it's the same thing that we just did. Okay, this would be person number 3 right here. Okay, and this would be person number 2, is a person number 2 over here, and this is person number 1 right here, and this is the person in the boat. So this is the boat person, right? So person number 3 is not moving, right? So they're going to see person number 2 just walking to the right, person number 1 just going straight up, and they're going to see the boat moving up and to the right. Okay. The boat is going to see person number 3 moving to the left. Is going to see person to the left moving opposite its direction, and it's going to see this person number 2 moving down, and person number 1 moving to the left. Right? Correct. So these are all really important. Relative motion is going to be really important. And putting yourself into different frames of reference is a good skill to have, okay? And it's going to become really important when we're doing projectile motion here in 1.5, because some objects may be moving at a constant velocity in one direction, but be speeding up and slowing down in another direction, right? So you have to consider frames of reference when you're doing those kind of transformations. Okay? So let's practice this again with another problem. You have a factory conveyor belt that is rolling down at 3 meters per second, and you have a piece of cheese that is directly in front of a mouse, and the mouse is moving straight at the cheese. Now, the mouse and the cheese are both on this factory conveyor belt, okay? This conveyor belt. And the conveyor belt is moving down, but the little mousey here is walking just to the right at 4 meters per second. So what does a person standing on a factory floor out here, not on the conveyor belt, but a factory floor here see as far as the mouse's overall speed on the conveyor belt with reference to the conveyor belt moving and the mousey moving at the cheese? Will the person see the mousey's overall speed as 1 meter per second, 2 meters per second, 3 meters per second, 4 meters per second, or 5 meters per second? Go ahead and pause the video and see if you could figure this out. Okay, so you've paused the video. So the frame of reference is going to be relative to a person standing here on the factory floor. So this is you. You're standing here. And you've got a little hard hat on to protect your noggin. Okay, anywho. So you're going to see this mouse moving to the right, but also simultaneously moving down. So the mouse is going to have an overall velocity of down and to the right as they move past you, okay? And so this this speed of this mouse is going to be to the right and down, so that's vector addition. You're doing tip to tail, right? And guess what this is? It's a 3, 4, 5 right triangle, right? So to get this, you just take the square root of the two sides, which is 3 meters per second squared. Well, it's actually negative because it's traveling in the negative y direction. This is in the positive 4 direction squared, plus positive 4 meters per second squared, and that's equal to 5 meters per second. Okay, so the answer should be E. And this is basically the transformation that you're doing, right? The mousey relative to the belt has a velocity of 4 meters per second. The belt relative to the factory floor has a speed of 3 meters per second. So the overall velocity of the mouse relative to the factory floor is going to be 5 meters per second. Okay. And here's another example in night. You have a police car chasing a bank robber, and the police car is driving at 50 meters per second, and they fire a bullet to shoot out the tires. Now the police, so the gun is going to shoot a bullet at 300 meters per second, okay, while the car is driving at 50 meters per second. Well, when they're going to pass by a TV camera crew that's parked on the side of the road. So how fast is the bullet speed relative to the camera crew? Well, let's do a reference frame. So let's draw a little reference frame for the camera crew. This is Y, and this is X. And the crew is standing right here, and they are not moving, okay? They have little cameras though. So they're going to see the car right here, okay? Driving little wheels and stuff, a little angled here, starting to look like happy face. Anyways, the car is going to be moving, well, the police car is moving at 50 meters per second upwards, right? But they are also firing a bullet out the window, okay? And that bullet is going to be moving at 300 meters per second. So the bullet is going to be moving, the speed of the bullet relative to the car is 300 meters per second. And this is the speed of the car, relative to the camera crew. And relative to the camera crew, what should we designate them as? Just parked. And so this is the parked people, parked, right? So the speed of the car relative to the parked people is 50 meters per second. the speed of the bullet relative to the car relative to its frame is 300 meters per second. So to get its overall speed for the bullet relative to the parked crew, you're going to have to add that 300 meters per second to the 50 meter per second, and that should be 350 meters per second. Okay, and so you have to consider that frame of reference is moving. So the bullet is a speed relative to a moving frame of reference. So the still frame of reference is just this. It doesn't have a prime, so that ends up being 350 meters per second. Okay. So now we're going to be dealing with two-dimensional and one-dimensional. Well, we're going to do some practice problems using the tutorials to get you started on the tutorials. Okay. So. And is frame of reference stuff, right? But we're going to be considering the frame of reference not moving, okay? But just to be clear, again, we're going to have two types of motion now, right? You're going to have a Y direction motion, so you're going to have a curve fit for the Y direction motion is going to be Y versus T, so that's this curve fit. And then you're going to have a velocity in the Y direction versus time curve fit, linear fit for right here. Okay. Well, you also have an X direction motion versus time fit, curve fit. And then you're going to have a velocity in the X direction versus time fit as well, which is what we've been kind of doing. We did that back here with the mousey. It had a velocity in the X direction, and it was on a conveyor belt moving in the Y direction, right? So we were kind of doing that, but we're using only constant velocities, okay? Well, now we're going to throw in accelerations, and now there's going to be an X direction acceleration and a Y direction acceleration, okay? So we're going to have to keep these equations of motion in mind, okay? So here we have a ball that starts out right here. So this is a lecture tutorial, so let's do some practice stuff on the lecture tutorials. So we have a ball that starts here at time 0, and then this is at 1 second, and this is 2 seconds, and this is 3 seconds, and this is 4 seconds, 5 seconds, 6 seconds, 7 seconds, okay? And what you're supposed to do is figure out its velocity in the X direction, is velocity in the Y direction, and its overall velocity. And then we're going to do some division. And usually, typically when you're doing this division that's setting you up, you would take the inverse tangent of this division of Vy versus Vx. So that's what this is supposed to be. It's kind of setting you up to getting theta, angle theta. All right? So here's what I want you to do. I want you to figure out its overall, so from time 0 to time 1, I want you to figure out what its velocity is from 0 to 1 seconds in the X direction and in the Y direction, and then what its overall velocity is. Okay? So go ahead and try this out. Okay? And just do from 0 to 1 second. Okay? All right. How'd you do? Well, the object moved down and to the right. So its overall velocity is this. So this is its overall velocity right here. Okay? Well, I can't measure that, but if each block is 1 block, and it's going from 0 to 1 seconds, in the first second, from 0 to 1 seconds, it moved 2 blocks in that 1 second. So it moved basically a distance of 2 blocks. And then in the Y direction, it moved down 1 block. So it had -1 block velocity. Okay? negative 1 block motion in that first second. So for the velocity in the x direction, it moved one block in that 1 second. And I feel weird by putting in b. Let's just call each of these blocks a 1 meter. Okay. So let's call this distance from here to here 1 meter. Okay. So in that first second, it moved 1 meter to the right and simultaneously moved 1 meter down. Okay. Well, that means it had a positive 1 meter per second, right? So it moved actually that's 2 blocks. Dang it, Jim, making some mistakes here. It moved 2 meters or 2 blocks over that first second, right? And it also moved down 1 block or 1 meter in that first second, okay? So to get its speed, again, to get this velocity in that first point in time, it moved, the velocity in the x direction would be its change in position, its displacement over time. Well, it moved from 0 meters to positive 1 meter from 1 seconds minus 0 seconds. And so that's how we got a positive 1 meter per second. Okay. And in the y direction, it had a displacement in the y direction, delta t, and that was negative 1 meters. It moved down 1 meter from where it was. That should be meters. From 1 seconds to 0 seconds. So that is negative 1 meter per second. Okay. All right. Well, to get the overall velocity, well, that's the hypotenuse. Well, that's going to be, to get the overall distance, I should say, and this is going to be, we're just going to call this r, to get that overall distance. So r is going to be equal to its displacement in the x direction squared plus its displacement in the y direction squared, right? Well, that is going to be the square root of positive 1 meter squared plus positive 2 meters, which, dang it, I did it again up here. I'm sorry. Those should be 2's. I apologize. So it'll be positive 2 meters squared minus 1 meter squared. Okay, so that's a total of 2 squared, so that's going to be 4 meters squared plus 1 meter squared. And that is what? 5? Square root of 5? What is the square root of 5? Well, we'll just keep it square root of 5 if you want. 2.24. So that's 2.24 meters. And it did that over the period of 1 second. So that'll be, it'll just be 2.24 meters per second. All right. Now, how would you categorize this? Would you categorize this as speeding up, slowing down, or constant velocity? Well, it moved the same distance here, 2.24 meters, over the next from 1 to 2 seconds, and then the same thing here, and then the same thing here, and the same thing here. So it looks to me that this object has no acceleration. So if it's moving down and to the right at a constant displacement in between each second of 2.24 meters, well, that means it's a constant velocity. So its overall velocity in the x direction is going to be positive 2 meters per second, and its overall velocity in the negative 1 in the y direction is going to be negative 1 meter per second. Now, to get this angle theta right here, so this is the angle theta right here. So it's moving down and to the right. and we're going to be getting this angle right here. Okay, so that angle is going to be Vy over Vx, right? So that's negative 1 over 2. So that's negative 0.5. That's just negative 0.5, right? And so we had to figure out what that angle is. Well, let's go to the calculator. So if that was theta, that would be 0.5, and that's negative. And then we'd do the inverse tangent of that. And that would be negative 26.57 degrees. So theta would eventually be, so that angle right here that it's making would be 26.57 degrees. And so that's why we're doing the Vy over Vx. Okay. Let's do another one, but let's do one with that has some acceleration to it. Okay. So now we're going to have to consider a frame where an object can actually be moving at a constant velocity in the x direction, but actually be speeding up in the y direction, right? So if an object was turning and it was actually it's turning, but the person had their foot on the accelerator and is turning at such a rate where it would be, starting here, it went to here, and then it went to here, right? And then it went to here. Well, if you track at this first second, so if this is 0 seconds, this is 1 second, 2 seconds, 3 seconds. Well, that means the object would be right here, and then right here, and then right here. After the first second, from 1 to 2 seconds, 1 second, 2 seconds, 3 seconds, right? And then from 0 seconds to 1 second, it's right there. Let me do something here. I'm going to remove this. And I'm going to put the 0 seconds right over here. So this is 0 seconds. Okay. And then from 0 seconds, 1 second. So this is the 1 second mark. So it went this far. And then now at the 2 second mark, it's gone a bit further, and then at the 3 second mark it's gone a bit further, right? So if you look at these dots, these arrows, these distances are increasing over time. So this is definitely speeding up in the y direction. But if you look at these dots here in the x direction, it's a constant velocity in the x direction, right? So if you're turning your car and you're kind of speeding, you're kind of accelerating as you're speeding your car, as you're turning your car, it's possible to actually have a constant velocity in the x direction because this vector is increasing only in the y direction, right? So let's practice this a little bit, and this is going to be this is one of the most important concepts that we need to wrap our heads around. In projectile motion, it's possible to have a constant velocity in one direction, and while simultaneously have an accelerated motion, speeding up or slowing down, in another direction. So that's what we're seeing right here. Okay. So let's practice this using a lecture tutorial, okay? So again, each block is 1 meter. So 1 meter by 1 meter, okay? Okay. So what I want you to do is you're going to have to do only from 0 seconds to 1 second. So this is the 0 second mark. This is 1 second. This is 2 seconds. This is 3 seconds. This is 4 seconds. And this is 5 seconds. So go ahead and write the overall velocity vectors for each one of these points. Okay? So try that right now. Okay? Alright, hopefully you paused the video and you've written those overall velocity vectors. So if I do that, I'm going to, you know what, I'm going to use the actual vector tool, drawing tool. So from 0, vector tool, having a hard time with basic skills. So the vector tool here is going to go from there to there in the first second, and the next second it's going to go from there to there, and then in the next second it's going to go there to there, and in the next second it's going to go straight there, straight down, and in the last second you go there to there. Okay, so from 0 to 1 second it looks like, let me use blue for this guy. In the x direction, I'm using blue as the x direction. It looks like it's traveling to the right. It looks like it traveled a distance to the right. And how many blocks is that? 0, 1, so it looks like 1 meter, 2 meter, 3 meter, 4 meter, 5 meter, 6 meters. So it looks like it's traveling a positive, so positive 6 meters. Looks like it's traveling a positive 6 meters to the right. Okay. And in the y direction, now, draw that vector. In the y direction, I'm going to use red for the y direction. It looks like it's traveling down -1 meter. Okay, and that's over that's just for that one time frame from 0 to 1 seconds. So without doing the math, you could see that in the first second it traveled a positive 6 meters in that first second to the right. So the answer to this part here would be positive 6 meters per second. Okay. And in the y direction, it traveled at -1 meter per second. Okay? And so overall, what you could say is that this is going to be, its overall speed is going to be positive 6 meters per second squared plus 1 meter per second squared. And that would be, what is that, 36 plus 1? So it would be the square root of 37 square root, which would be 6.08 meters per second. So this velocity vector right here is 6.08 meters per second. And we can figure out the angle if we want, but that's kind of not what we're asked to do. We want to do now the velocity in the x direction and y direction between 1 and 2 seconds. So let's go ahead and do that. Okay. So let's begin drawing another blue arrow. So this blue arrow looks like it's going to go, it looks like this guy is going from this box to this box, and X direction is blue. I'm going to move this guy up a little bit. So it looks like it's traveling in the next second, 0, 1, 2, 3, 4. So that would be positive 4 meters in that next second. So there's a little bit of a change. It was going 6 meters per second from 0 to 1 seconds, and now it's going positive 4 meters per second in the next from 1 to 2 seconds. Okay, well, let's see what is its displacement vector is in the y direction. Okay, well, let's get an arrow. We're going to draw an arrow. And it looks like it's traveling down. It looks like it's traveling down a displacement of -2 meters there in that case. That would be red. So -2 meters. In this next second, right? So to fill in the blanks here, let's go ahead and we're going to fill in the blanks here. In that next time frame, it looks like it's traveling a positive 4 meters per second and a -2 meters per second in the next time frame. Well, now we have enough information to figure out what is its acceleration in the x direction, right? Well, to get the acceleration in the x direction, you're going to do final velocity minus initial velocity over delta t, right? Well, that final velocity is going to be positive 4 meters per second, and that initial velocity is 6 meters per second. Correct? And that time frame is from 2 seconds to 1 second, right? Right? So that acceleration vector started occurring right here. So that means this is going to be, what is that, -2, right? It looks like the velocity, initial velocity vector got reduced by 2 meters over that 1 to 2 second time frame. So again, the reason why we're doing 2 seconds minus 1 second instead of 2 seconds minus 0 seconds is that initial velocity occurred right here. So now at this point you're applying an acceleration vector at the 1 second mark, which is going to alter the velocity from the 1 to 2 seconds. So that's the reason why this is over the period of 1 second. Okay. In the y direction, you're going to be doing the same thing. In the y direction, you started out at -1 meters per second, and now you're traveling at -2 meters per second. Well, that means you've just added a y direction velocity vector down. And then you square those guys because it has to be an acceleration. So it looks like whatever this acceleration vector is, it's got 2 components, right? It looks like it's going to have a turning component, and it's also going to have a slowing down component. So let's actually map that. Let's map that right here at the 1 second mark. And it's going to have, all right. Let's actually use, I don't know why I did that there. We're going to use an arrow to represent this overall acceleration vector. Well, this overall acceleration vector is going to have to be pointing in the negative. It's going to have to pointing in the negative direction by 2 blocks and pointing down by 1 block. So I'm going to use this as purpley. Is that purple? Would you call that purpley? That looks a little too close, so I'm going to use pink. Like pink. All right. So that means this acceleration vector, okay, has components of -2, and also in the x direction, -2 meters per second squared and -1 meter per second squared. So it's taking away -2 meters per second over 1 second at this block here. Okay. So its overall acceleration vector now, to find out what this number is right here, what that acceleration vector is right there, that is going to be, the overall acceleration is going to be the square root of ax squared plus ay squared. So that acceleration is going to be, what is that? 2 squared plus 1 squared, so was that -2 squared minus 1 squared, so is that, what is that? 5, square root of 5. So this will be square root of 5 meters squared per seconds to the 4th, which is then going to be, what is that, calculator wise? Come on, calculator. I think we did this before. Was that 2.23 or something? Square root 2.24. 2.24. So that acceleration is going to be 2.24 meters per second squared. Okay. Let's erase this. So that's the length of that arrow, 2.24. Okay. And so the cool thing about this is this vector right here, that pink vector, that is a constant acceleration vector. That is going to be added to each one of these guys. That is changing the nature of this guy and causing it to eventually turn. And so that acceleration is not only slowing it down in the x direction, but it's speeding it up in the y direction simultaneously. Because notice it's acceleration vectors in the y direction, right? It's acceleration vectors in the y direction is actually increasing in size every time by 1 block down, or by 1 meter down. Right? Until finally, in the end, it looks like it's 1, 2, 3, 4, 5. It's going to have a -5 displacement down. In the x direction, it's getting smaller by 1 meter every time, until it actually comes, by 2 meters every time. It's getting smaller by 2 meters every time until it comes to a stop right here. And now it's going to be turned around. So it's basically slowing it down in the x direction and then turning it around. So it's going from slowing down to speeding up in the x direction, and it's just constantly speeding up. It's just speeding up only in the y direction. Okay. Well, this is relative motion that we're now leading into two-dimensional motion. Okay. So in the next part, what we're going to do is just study projectile motion. Okay. I hope you had fun. Bye.